Hello and welcome to NHP's webinar on safety input devices and applications. My name is Daniel Nathanson. I am a commercial engineer for NHP Electrical Engineering, specializing in automation and integration products and solutions, and also a TUV Rhineland accredited functional safety engineer. This is just one in a series of webinars created to showcase NHP's smart devices, powered by smart distribution and embedding smart safety into operational processes, providing our customers with better visibility into processes, data, and analytics. In this session, we will specifically be looking at interlock switches, their application, special functions, and specific guidelines and rules for how they should be used, with respect to the machine safety standards. The purpose of an interlock switch is to detect whether or not a movable guard is opened or closed. This guard is used to protect persons from a hazard produced by a machine. Interlock switches are particularly useful for applications where the guard needs to be removed for regular operation or maintenance of the machine, where taking off fixed guards with the use of a tool is impractical or wasteful in terms of time and effort. The interlock switch interacts with the machine via electrical signals, or in combination with pneumatic, hydraulic, or even mechanical devices, and is fitted directly to the guard to ensure that direct monitoring. The ultimate purpose of the interlock switch is to make sure that the machine is not in a hazardous condition if the guard is opened, and prevent the machine from going into such a condition while the guard remains open. Only when the guard is closed can the machine be started. The standards for safety of machinery provide all the necessary guidance for the design and selection of interlocking devices. The main standard series used in Australia and New Zealand is AS/NZS 4024, of which Part 1602 directly addresses interlocking devices, and is the standard which this session will be focusing on. It covers the operating principles and the different forms and types of interlocking devices, both with and without the ability to keep the guard closed. It also covers requirements for design, selection, and installation of the switches to minimize the possibility of defeat and ensuring the integrity of the overall safety system. The standard, of course, is intended to be read in conjunction with the rest of the AS/NZS 4024 series for safety of machinery, which also includes the requirements for risk assessment, safety categories and performance level, and other guarding and control measures as required. Part 1602 is a direct text adoption of the international standard ISO 14119, the 2013 edition, which brings them in line with what we should see on machines coming in or destined to be shipped out to the rest of the world. The standards describe 4 general types of interlocking devices, which should appear familiar to you. If not, it's best to refer to our Safety Essentials series Part 2, where we take a look at some of the products and devices used in machine safety. Type 1 and Type 2 switches make physical contact with the guard, whereas Type 3 and 4 are non-contact. The differences between them are whether or not the actuator is coded or unique. Each type has their own advantage and disadvantages, and depending on which one is used will have a certain design and installation requirements. This is Table 1 from Part 1602, which provides an overview and examples of the various types of interlock devices. I've highlighted in grey the examples where NHP have a suitable safety product offering. As mentioned in the previous slide, Type 1 and 2 make physical contact with the guard. The difference is the coding. For example, a Type 1 switch being an uncoded device means that literally anything can physically come in contact with the switch and actuate it. Typically and most commonly, these are limit switches, which the guard press on to indicate their position. Type 2 device uses a coded actuator. The most common example is a tongue interlock switch, where the actuator is a unique shape so that only it can engage with the switch. This is therefore a two-piece design where a separate actuator needs to be mounted to the guard. Type 3 and 4 are non-contact interlock switches, whereby the guard does not necessarily make any physical contact with the switch. Again, the only difference is the coding. Type 3 are uncoded, meaning that anything can actuate the switch depending on the technology. For example, a magnetic reed switch is actuated by a magnet, so your finger won't be able to switch it. However, it would if it was a capacitive or ultrasonic sensor. And Type 4 are non-contact but require a coded actuator, such as a coded magnet or an RFID actuator. These require a specific type of actuator rather than run-of-the-mill components. This is an example of a Type 1 interlocking device. In this case, a roller plunger limit switch is fixed to an enclosure with a hazard inside. The lid has a rotary cam attached to it, which is what presses against the limit switch. As you can see from the animation, when the lid opens, the cam rotates and pushes down on the switch, disabling the machine. When the lid closes again, the limit switch is released and the machine is able to be started again. Some features of this application example are that the lid directly operates the contacts of the switch. This is called direct mechanical action and forces the contacts open. The arrangement of the limit switch underneath the rotary cam ensures that it is impossible to have the lid open and the limit switch not pressed. The only way to do this is to physically remove the switch from the enclosure, which requires the use of special tools. However, there is possibility of a dangerous failure if, for example, the actuator breaks off, or if there is misalignment between the cam and the switch, such as when the switch is removed. Also, if the lid of the enclosure can be removed from its hinges, then there is no way that the switch can detect this, so the lid needs to be removable only with special tools. This is the same application example, but this time using a Type 2 device, a tongue interlock switch, which uses a coded actuator. This is a much simpler design as there is no requirement for a specially designed and installed rotary cam. All that is needed is for the actuator to be fitted to the lid. Again, the actuator has direct mechanical action on the contacts inside the switch. However, the actuator needs to be aligned near perfectly with the switch to avoid damage from misalignment. If the actuator breaks off inside the switch, for example, then the switch can fail to detect the lid opening. The mounting arrangement of the switch can also be a problem, as the actuator opening can accumulate dirt and debris, which can degrade the mechanism inside the switch. And lastly, the actuator itself could cause harm to persons. Imagine the lid coming down on someone's hand. The actuator could do some damage. The same application again, this time using a Type 3 device, for example a magnetic reed switch. This application has the advantage over Type 1 and 2 in that it does not require any physical contact with the switch and can be completely sealed. No liquids or debris getting into the switch housing. This is also much more resilient to misalignment and can be actuated from different angles. This lends itself to a variety of different applications other than the one shown. It is uncoded, however, meaning that you can take any old magnet and press it up against the switch to defeat it. And in the case of reed switches, they are susceptible to shock and vibration, which could nuisance trip the safety control circuit. And lastly, the same example with a Type 4 device. This one uses an RFID coded sensor and actuator. These are completely solid state with no internal moving parts, which makes them highly resistant to shock and vibration. They are completely sealed, so are useful for washdown or dusty areas, tolerant to misalignment, broad actuation angles, etc. Where the Type 4 devices really stand out is in their ability for the actuator to be coded, so you need to have the correct RFID actuator in place in order to actuate the switch. The only real physical disadvantage of this type of device is that the electronics used inside them may be affected by nearby electrical noise, for example from nearby power wiring, variable speed drives, surges, transients, etc. Type 1 switches can have direct mechanical action or non-direct mechanical action. Direct mechanical action means that the physical act of opening the guard directly forces the contacts of the switch. This can also be referred to direct opening action when concerned with electrical contacts. The main distinction for direct mechanical action is that only rigid components are used to engage the contacts, for example, no springs or elastic materials. If using only one interlocking switch, either Type 1 or 2, it must have direct mechanical action with the guard, and the contacts in the switch must be opened via direct opening action. If using non-direct mechanical action, such as opening the guard releases the actuator on the limit switch so that only the force of an internal spring operates the contacts, it's not sufficient to have just the one interlocking switch. You need to have a second one on the same guard, which operates with direct opening action. Having the two switches with diverse mechanical action can help with fault detection and avoiding common cause failures. This animation shows the application of two Type 1 limit switches arranged on the same guard with diverse mechanical action. The one on the left is non-direct and the right is direct. When the guard opens, the non-direct action switch is released and relies on the spring to open the contacts and disconnect the control circuit, whereas the direct action switch is forced to close as the guard moves over it. The force of opening the guard is directly responsible for forcing the contacts open. But what happens when there is a single fault in one of the switches? A good example, is where the spring fails inside the contact block of the switch on the left. When the guard is open, there is nothing there to open the contacts. If this was the only switch used on the guard, then this could lead to a dangerous state. However, the switch on the right does not rely on a spring, so the circuit is still disconnected with the guard open. This also allows for the control system to detect that one of the switches failed to open. It can then be used to inform the operator and prevent startup of the next cycle until the switch is repaired or replaced. The fundamental requirement for interlocking is to prevent the machine from being in a hazardous state while the guard is open. The same can be said for the reverse, where the guard is prevented from being opened while the machine is in a hazardous state. This brings with it the requirement for guard locking. The principle for this requires a guard to be locked and requires an external signal to unlock it. Only when it is unlocked can it be opened. Meanwhile, the control system is checking the state of the guard to ensure open or closed, and whether it is locked or unlocked. From this animation, you can see that there is a locking pin which is preventing the cam from moving and the guard actuator from being removed. An unlock signal is given and the locking pin is retracted, allowing the cam to move freely and the actuator can be removed. Once the actuator is removed, the cam is arranged so that the locking pin cannot be reinserted. So in order to lock the guard first, it needs to be closed. There are two types of guard locking applications. Unconditional unlocking is where the unlock signal can be given at any time, but when the signal is produced, it also has to send a stop command to the machine. The time taken for the machine to cease hazardous motion needs to be shorter than the time taken between sending the unlock command and opening the guard. This is only useful where the stopping performance of the machine is known and you can design around it. If you don't know the stopping performance, or it can change depending on the process, then you want to have conditional unlocking. This requires active monitoring of the state of the machine so that the guard only unlocks when the machine has reached a safe state. This is an example of unconditional locking. When the switch is turned to the unlock position, the guard locking switch is unlocked immediately and a stop command is given to the machine. When the unlock command is given, the guard can be opened at any time by the operator, but it should be that the time the guard is opened, the machine has already slowed to a safe state. For conditional locking, when the switch is set to unlock, a stop command is given to the machine before the guard locking switch is energized. Only once the machine has slowed down sufficiently is the unlock signal produced and the guard can be opened. How you know when the machine is slowed down sufficiently can be done by external monitoring, such as direct speed monitoring or indirect back EMF monitoring, or by putting in a sufficient time delay. Keeping the guard locked during hazardous motion is all well and good, but the lock needs to be strong enough to withstand any reasonably expected forces. For example, someone pulling on the guard really, really hard, or even material being ejected from the process and hitting the guard. For this reason, all guard locking devices have a quoted holding force, which needs to be higher than the forces expected upon the guard. You do not want to exceed the holding force. The result could be the guard being forced open and personnel exposed to hazardous motion. Guard locking devices are available in a variety of holding forces to make sure that you choose one that is right for the application. We discussed earlier the different types of interlocking devices, some with coding and some without. The reason for coding is the idea that an interlocking system could be defeated. How easily this can be done depends on the defeasibility of the system and the different measures taken to prevent this from being a problem. For example, having spare actuators is good from a maintenance and replacement perspective, but how easy is it for someone to defeat the safety interlocking if they have a spare actuator? The simplest concept behind preventing defeat of the interlocking system is to remove the motivation to defeat it. Start with the process and initial design of the machine. Is it possible to design the machine such that there is no need for anyone to want to open the guard during operation? Easier said than done in a lot of cases. Fortunately, the standards have a step-by-step process for analyzing and preventing defeasibility. This is the step-by-step guide. A. Firstly, basic design and selection of the interlocking devices. Make sure that they are sufficiently protected against inadvertent change and are secured in their positions. Use reliable fasteners that require a special tool, protect them from damage and breakage, prevent them from self-loosening using Loctite or similar adhesive. Use a combination of direct and indirect mechanical actuation, etc. B. Check whether the motivation to defeat the machine, as far as what is reasonably foreseeable, is present. Look at the tasks and people involved in the process. Do a risk analysis. C. If there is a task which can carry with it a motivation to defeat, do what you can to the process to try and eliminate it. Implement design changes or alternative modes of operation. D. And finally, if you can still see there is reasonable foreseeable motivation to defeat the system, there are additional measures which are required. These are the additional measures. Select or install the interlocking devices such that defeating in a reasonably foreseeable manner is prevented. This can be done by simply mounting the interlocked devices out of reach or otherwise physically preventing someone from accessing the device. Mount the switches behind the guard so that to access them the guard needs to be opened first, stopping the machine. Or even better, mount them behind the guard and also behind a physical shielding so that even while the guard is open, you still can't access the switch. Otherwise, prevent the switch from being actuated from readily available objects. This can be done by using a coded actuator, as mentioned in the device types, so that only the actuator associated with the switch can be used. But as we mentioned, we can have spare actuators, so increasing the level of coding can be done so that only a specifically unique actuator can be used. The different levels describe the number of different unique actuators that are available to the operator to purchase. A high-coded actuator, for example, is a random one in over 1,000 different codes, making it increasingly hard to get a spare actuator to work without some form of pairing or teaching. Another method is preventing the switch from being removed, repositioned, or otherwise detached from its original position. You could do this by using permanent means of fixing like welding, gluing, one-way screws, or riveting, for example. This may cause problems when time comes to replace the switch, however. Or put in automated measures which prevent defeating so that simply actuating the switch does not necessarily allow the machine to operate. For example, the switches can only be actuated in a specific sequence or during specific periods within the machine process. This is all done via automated systems, so a safety PLC is almost always required in this example. And lastly, checking for plausibility. This requires the use of two different actuation modes, which require multiple separate actions to defeat the system. For example, using two different types of interlock switches, which are located in different areas, such as direct and indirect mechanical operation switches on different ends of the guard, as we saw earlier with the limit switches. One such example of cyclic testing involves incorporating a test to ensure that the interlocking devices are working correctly before allowing the machine to start. Here we see the control station prompting the user to cycle the interlock switch contacts by opening and closing the guard. Only once this has been performed and the switches are deemed healthy is the user able to restart and start the machine. Depending on the type of interlocking devices used, there are some mandatory and recommended practices which are used to manage defeasibility. For Type 1 and Type 3 devices, limit switches and uncoded non-contact switches, it is mandatory to apply at least one of these measures. Mount out of reach, physical obstruction, hiding it, status monitoring or cyclic testing, or non-detachable fixing. It is also recommended that an additional interlocking device is used for checking plausibility, that is, an extra limit switch with indirect mechanical action. For hinged Type 1 devices, such as the one which operated off a hinge cam in the very first Type 1 example, both the actuating cam and the switch must be non-detachable. Type 2 and 4, tongue interlocks and coded non-contact, also require one of the top four measures in the case of low and medium coding. For high-level coding, you only need to have a non-detachable actuator. And for trap key systems, you must also have non-detachable actuators and switches. As the guard interlock is part of a safety system, it needs to be addressed as part of the overall safety control system. This means that there are certain control requirements and fault assessments which need to be adhered to. This, of course, depends on the standard used. The three main ones are for categories, performance level, and SIL, which we saw in the first Safety Essentials series. In any case, where you are using multiple interlocking devices for redundancy, you need to manage the likelihood of common cause failures, and of course consider the electrical and environmental conditions which may affect the equipment used for interlocking. When designing for a high risk application like Category 3 or 4, PLE or SIL3, then there needs to be some level of hardware fault tolerance. This means that in the event of a hardware failure, then the safety system can still perform. A hardware fault tolerance of 1 means that the system can tolerate one hardware failure. However, 2 failures may lead to a loss of the safety function. Typically, a hardware fault tolerance of 1 is realized as 2 interlock switches on the one guard, or one switch with 2 sets of contacts. If one switch or contact set fails, the other one is there as a backup. There also may be a requirement for some level of automatic monitoring of the interlock switches to provide some level of diagnostics. In the event that the switch fails, the safety control system needs to know about it and perform accordingly to bring the system to a safe state, but also to alert the operator of a fault. This can be done using safety monitoring relays or safety PLCs. The level of diagnostics required depends on the frequency of access through the guard. If the guard is only operated rarely, there is a chance that multiple faults could develop over time between operations of the guard. So in this case, additional measures may be required, such as cyclic testing, to ensure that the guard is properly monitored. If manual cyclic testing of the guard is required, then there is some guidance in the standards on how often this should be performed. For the highest risk applications, like PLE, then you should cycle and test the guard switches at least once every month, whereas a lower risk application, PLD, then at least once every 12 months. It is recommended that the control system keeps track of the process and prompts the operator to perform the manual checks at the appropriate intervals. Common cause failure is what can occur to redundant devices if a single fault can cause both to fail in the same way at the same time. If this happens, it doesn't matter how much redundancy you have, the one fault has knocked out your entire safety system. Diversity is one of the best methods for ensuring common cause failure is managed effectively. This typically comes in the form of using two different interlock devices of different technologies or even actuating methods. Again, mixing direct and non-direct mechanical action. The likelihood of the same type of mechanical fault, which pushes down on one actuator and releases the other whilst the guard is closed, is near impossible. But other types of diversity are available depending on the design. For hydraulic or pneumatic-based machines, multiple interlocking devices can be used to isolate electrical power, but also to close a valve to isolate any hydraulic or pneumatic power. And finally, electrical and environmental conditions should be taken into account when selecting the appropriate interlocking device. This almost goes without saying. Ensure that the device is suitable for the environmental conditions it will be situated in, temperature, humidity, etc., but also the electrical requirements. If the switch is driving a load directly, then ensure the contacts are capable of switching the load. Be familiar with the utilization categories for the load, as well as voltage and current requirements. For electronic devices such as Type 3 and 4 switches, make sure that there is adequate protection against the effects of electromagnetic interference. Make sure everything is sufficiently earthed. Run the control wiring separate from the power wiring. If there is a VSD nearby, make sure its output is using shielded cabling, etc. And so concludes today's presentation on interlocking switches. By now you should have some more intimate knowledge on the function and various types of interlocking switches and devices, their applications, and some of the special requirements with respect to the machine safety standards. For more information on the selection or even just on machine safety in general, there is a wealth of information available in the NHP Machine Safety Selection Guide. I also highly recommend reading through Rockwell Automation's Machinery Safe Book 5, which is a bit more advanced but provides fantastic guidance around designing and navigating machine safety control systems. Thank you for joining us for this webinar. I hope you found it beneficial, and if you'd like to watch it again or to find more webinars in this series, please go to nhp.com.au or our dedicated NHP YouTube channel. If you have any further questions about machine safety products and solutions, please contact your local NHP sales representative. With smarter and faster decision making and seamless connectivity spurring new collaboration, NHP is enabling the connected enterprise. See you next time.